Hello and welcome to the part 2 of IC voltage regulator and SMPS. Myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology, Bhinder. So in this part 2 presentation, we'll see the LM317 IC voltage regulator, and secondly we'll see the SMPS with respect to block diagram, working principle, specification, special features, advantage, disadvantage and applications. And thirdly we'll say the use of heatsink for regulated power supply. And course outcome: after completion of this presentation, we will be able to, or the learner will be able to maintain IC voltage regulator and SMPS, that is the course outcome expected. And unit outcome expected as stated earlier, the 4 points. So now let's see the LM317 voltage regulator, that is a variable voltage regulator, its circuit diagram and working. So basically, as we see in the circuit, in the given image or photo, that is LM317 is a 3-pin IC, a 3-pin voltage regulator with the first pin as a adjustment pin and second pin as the output voltage and third pin as the unregulated input voltage. So it is basically a positive linear voltage regulator used for floating, as there is no ground point, and floating voltage regulator it was invented. The LM317 voltage regulator was invented by Robert C. Dobkin and Robert J. Widler while working for National Semiconductor Company in the year 1970. It is a 3-terminal adjustable voltage regulator and is easy to use because to set the output voltage we need two resistors, external resistors R1 and R2, and moreover we connect a fixed resistor between the output and adjustment of the LM317 regulator, then it can function as current regulator. The second diagram down we see is the internal block diagram, in which we see the Darlington pairs acting as a series pass element, and the output voltage is compared with the internally generated voltage reference to produce an error voltage which drives the Darlington transistor to regulate the output voltage. Moreover, down here the R limit resistor is the internal sensing resistance. The voltage across it is proportional to the load current. So this voltage is applied to the internal protection circuitry, and if the load current exceeds beyond its maximum value, the Darlington pair will be automatically turned off to protect the IC. So LM317 is monolithic IC voltage regulator with an adjustable output voltage which can supply more than 1.5 ampere of current to the load, and the output is adjustable. Output voltage is adjustable from 1.2 volt to 37 volt. So there is inbuilt thermal overload protection and short circuit current limiting constant with the temperature, and the LM317 voltage regulator are available in package as a 3-lead transistor, or it is available in TO220 plastic package, or as a surface mounted D2 pack 3. So here is the circuit arrangement for adjustable voltage regulator using LM317, in which we see the unregulated DC input is given to pin number 3 and regulated output is taken from pin number 2, whereas pin number 1 is the adjustment pin. Then we see capacitor C1 and C2 as the input and output filter capacitors, and there is R1 resistor and R2 resistor. R1 is a fixed resistor of 240 ohms, that is acting as a current set resistor, and The R2 is a variable register port that is acting as output set register. So when it is properly configured, then LM317 produces a voltage of 1.25 volt between its output and adjustment terminals. So it will be equal to the V reference that is internally generated, and that V reference is 1.25 volt. Moreover, in practical regulator, we can connect one diode here between pin 2 and pin 3. Diode can be connected. Another diode can be connected between or parallel to R1, and down here at the second end of the R1 we can connect one capacitor of 10 microfarad. That will be a more practical. So the diodes connected across pin number 2 and 3 and across R1 is to block any discharge current or due to the internal low point inside the high voltage regulator. So LM317 regulator can provide excess output current, and hence with this capacity it is conceptually considered as an operational amplifier. So adjustment pin is the inverting pin of the amplifier, and to produce a stable reference voltage of 1.25 volt, an internal band gap reference is used to set the non-inverting input, and the output pin voltage can be continuously adjusted to a fixed amount using a resistive voltage divider between the output and the ground, which will configure the operational amplifier as a non-inverting amplifier. So a band gap reference voltage is used to produce constant output voltage irrespective of the changes in its supply power. So it is called a temperature independent reference voltage, frequently used in integrated circuits, and the output voltage of LM317 ideally will be V out is equal to V reference multiplied with 1 plus R2 by R1. So since R1 is fixed value of 240 ohm, so it is output voltage is mostly dependent upon R2, that is a variable port of 3K, 2K or 5K can be used, and an error term is added because some quiescent current or adjustment current flows from the adjustment pin of the device. So the above equation becomes V out is equal to V reference multiplied with 1 plus R2 by R1 plus IQ into R2, or that is I adjust into R2. So since the IQ or the I adjust leakage current is of 100 microampere or lower order, so the second term IQ into R2 can be neglected. So if we replace the low side register of the divider from the LM317 voltage regulator circuit diagram with the load, then the resulting configuration of the LM317 regulator will regulate the current to the load, and hence it will be acting as current regulator circuit. The output current is the voltage drop of reference voltage across the resistance R1 and is given as output current in the ideal case will be V reference by R1, but considering the quiescent current, the output current is given as V reference by R1 plus IQ. So the output current, that is I2, is nothing but the sum of the current I adjust plus I1, that is V1 by V reference by R1. So considering the heat generated inside is a major factor, and if the voltage difference increases, then the power wasted will increase, and this power wastage could be more than the power supplied. So heat consideration has to be done while designing. Now let's see the switch mode power supply, SMPS. Switch mode power supply basically it consists of the input rectifier and filter, high frequency converter, that is a switching device, and output rectifier with the filter, and there is a feedback path circuit through which the control signal or the signal to turn on and off the switch is used. So a pulse generator provides for the working principle, a pulse generator provides rectangular pulses to the control terminal, that could be the base or the gate terminal of the transistor or say MOSFET of an electronic switch, and due to this rectangular pulses it will turn on and turn off the transistor, and thus unregulated DC is converted to regulated DC, and the average output voltage V out will be dependent upon duty cycle D into V in. So duty cycle is, since duty cycle is defined as the on time of the pulse to total time, on time plus off time, so it is dependent upon the duty cycle. So by varying this duty cycle or on off time, we can vary the output voltage. So the block diagram we can explain with the input stage. The AC input supply signal 50 Hz is given directly to the rectifier and filter circuit combination without using any transformer. So this output will have many variations, and the capacitance value of the capacitor should be higher to handle the input fluctuations. This unregulated DC is given to the central switching section of SMPS. Now the central section of this SMPS, switching section of the SMPS, is a fast switching device that consists of either a power transistor or a MOSFET, and it turns on and off according to the variations, and this output is given to the primary of the transformer present in this section. So the transformer used here are much smaller and lighter ones, unlike the ones used for 60 Hz supply. These are much efficient, and hence power conversion ratio is also higher. So output stage, the output signal from the switching section is again rectified and filtered to get the required DC voltage. This is a regulated output voltage which is then given to the control circuit. So there is a feedback path control circuit which is a feedback circuit, and the final output is obtained after considering the feedback signal. So now control unit or the feedback circuit has many sections. The output sensor senses the signal and joins it to the control unit. The signal is isolated from the other section so that any sudden spike should not affect the circuitry. V reference input along with the signal to the error amplifier, that is acting as comparator, will compare the two inputs. So by controlling the chopping frequency of the high frequency chopping circuit, transistor or MOSFET, the final voltage level of the output can be controlled or maintained, and this is controlled by comparing the inputs given to the error amplifier, whose output helps to decide whether to increase or decrease the chopping frequency. And for this, pulse width modulation oscillator is used. So here we see the functional block diagram of SMPS, in which AC main is provided to the input rectifier and the filter circuit, so that we get the pulsating DC, and this pulsating DC is then applied to the switching device. The switching device is having input from the pulse with the PWM oscillator that will turn on and off the transistor, and that acting as a high frequency switch, or the chopping function is done by the high frequency switch and converting the pulsating DC into rectangular pulses, and the power transformer increases the power level of the output, and then it is applied to the output rectifier and the filter circuit, which produces more smooth or constant output voltage. And output voltage is feedback, a fraction of it is feedback for controlling purpose. So that is explained or depicted in the functional block diagram of the SMPS. Now, what are the important points to be considered or noted for the SMPS? SMPS circuit is operated by switch and output voltage varies. Therefore, the switching device is operated in either saturation or cutoff, and output voltage is controlled by the switching time of the feedback circuitry, and switching time is adjusted by adjusting the duty cycle, and it has high efficiency as the instead of dissipation of excess power as heat, it continuously switches its input to control the output. Now let's see the special features of SMPS. The transistor is operating as a switch and switching at a frequency of 25 kilohertz or more, and since it is operating in switching mode, power loss will be less and efficiency will be higher. Regulation, that is line and voltage regulation, will be very good, and speedier response. But radio frequency and EMI, radio frequency interference and electromagnetic interference, are high in SMPS. Weight is light with moderate cost. Now, what are the advantages of SMPS? Efficiency could be of the range 80 to 95% in some cases, and since less heat is generated, as less power wastage is taking place in the series pass transistor, which is acting as a switching element rather than active linear region. So there is less wastage of power, and it reduces the harmonic feedback into the supply mains. The device is compact as the size of the filtering circuits, inductor and capacitor at a high operating frequency is smaller, and the manufacturing cost is reduced due to this lower LNC, a smaller LNC. Provision for providing the required voltage is there in SMPS. Now let's see the specifications. Some of the specifications stated generally are DC output voltage, whether it will provide plus 12 volt, plus 5 volt, plus minus 15 volt, etc. And maximum load current capacity is stated, switching frequency is stated, output power is stated, battery operated or mains operated, it will be mentioned, magnitude of the radio frequency or electromagnetic interference will be mentioned, and power efficiency, load regulation, our voltage and our current protection. These are the specifications that manufacturers generally state. Disadvantage in SMPS includes the noise due to the high switching frequency of the transistor or MOSFET. The circuit is more complex, and there is production of electromagnetic interference and radio frequency interference. Now, what are the applications of SMPS? There are different application areas, like it is used in the motherboard of computers, laptops, it is used in mobile phone chargers, high voltage DC measurement, battery chargers, central power distribution, motor vehicles, consumer electronics, security systems, space stations, and many more. Now types, it can be of 4 types: a DC to DC converter, AC to DC converter, flyback converter, forward converter, or isolated or non-isolated SMPS. Now let's see the heat sink, its use in regulated power supply. So there are different types of heat sinks: extruded, bonded, fin type, or folded fin type, or we can employ active fan, a fan to keep the transistors or junction temperature under control, or even for a small regulated power supply we can make use of stampings with the transistor, or for SMD devices cross cut are used. So voltage regulator, since voltage regulators are making use of a power transistor inside it for either series pass transistor or in active region, or in switching operation where it will be operating in saturation and cutoff. So there is some voltage developed across the on transistor and current flowing through it, say the collector current is flowing through it. So that voltage and current makes certain power dissipation in the device, transistor device, and that power dissipation is given as VCC into IC and expressed in terms of watts, and this power dissipation is coming out in the form of heat. In the adjacent figure we can see the transistor LM317 connected to a heat sink of aluminum with the black color. The size of the heat sink depends upon the junction temperature that is developing. So maximum power handling capacity depends on the junction temperature as specified by the manufacturer. So a heat sink is a large metal piece of different shapes that we have seen, on which a regulator IC is mounted to radiate heat into the air, surrounding air, more quickly and easily. So in that way it is maintaining the temperature of the transistor, power transistor, under critical condition. So here there is no electrical contact between the transistor and the heatsink, though it is mounted on it. Why? Question is why aluminum is preferred for the heatsink and why it is painted black. So we know aluminum is a very good conductor of heat, and it is also cheaper and easily available in the market. And second reason for its painted black is due to black color, it is absorbing all the almost say more than 50% of the heat generated at the transistor and dissipating it to the surrounding. That's why aluminum is preferred. So thank you very much for patiently listening this lecture.